Hello guys, welcome back. This is our second problem, Bryton, and we are gonna solve this problem, which reads a stationary gas turbine power plant operates on a simple ideal Bryton cycle with air as a working fluid. The air enters the compressor at 95 kilopascal and 290 Kelvin, and the turbine at 760 kilopascal and 1100 Kelvin. Heat is transferred to air at a rate of 35,000 kilojoules per second, and we are asked to determine the power delivered by this plant. This is the net work, but we need to do it assuming constant specific heats at room temperature and constant specific heats, not constant, they change with temperature. So it is an exact analysis. So what we have, let us choose now different color. This time we're going to use green. So we have we are asked to get a network, which is the work of the turbine minus the work of the compressor, but it's also, this is power, sorry, but this is also Q in minus Q out. Well, we are going to use this since we already have Q in. So from first law analysis, for the heat addition process, we know Q in is the mass flow rate times the temperature, the enthalpy difference, which will be H3 minus H2, and Q out will be the mass flow rate times H4 minus H1. We don't know mass flow rate, but we can, if we can get to know each of the enthalpies, we can get mass flow rate from this expression above. Since we know Q in, now we have T1 and T1 and T3, so we know already H3 and H1, so the whole problem will get to know H2 and H4. So we're going to do it first for constant specific heats, and for constant specific heats, recall that H will be CPT. So we need to find out T2 and T4. In order to do that, we are gonna use we're gonna invoke isentropic expressions. So T2 over T1 equals P2 over P1 since for constant specific heats we know that K equals 1.4 and CP kilojoules per kilogram. Solving for T2 and substituting, we find that T2 equals 525.31 Kelvin With this temperature we can get the mass flow rate. Mass flow rate will be Q in this difference of H3 H2 will be Cp T3, which is given. T3 minus T2 that we just found. So substituting this mass flow rate is 60.60 kilograms per second. Now, similarly, we can use T4 sorry, we'll need to just discover this. So we can use T4 over T3 to be P4 over P3 again, solving for T4 and substituting the values. We get T4 to be 607.24 Kelvin. So we can find Q out. And recall that that will be mass flow rate, this mass flow rate, times Cp, the Cp, times T4 that we just found, minus T1 that we were given. This would be 19,320.67 kilojoules per second. So finally, W net will be Q in minus Q out, which will lead to 15,679.32. So this is our first answer. We mark it. And now we go to solve it with variable specific heats. I'm going to change the color a little bit so we have a difference. So this time we're going to do it with variable specific heats. That is table A17. So From table A17, we know state 1 at 200 K, we can get H1 to be 290.16 kilojoules per kilogram, and PR1 to be 1.2311, and at 1100 Kelvin, which is a state 3, we can get H3 to be 1161.07, $167.1. So we're gonna solve PR2 over PR1 equal to P2 over P1. Remember, P2 is 760, P1 is 95. So solving for PR1, we have, and substituting, sorry, for PR2, and substituting will be 9.8488. By interpolation, we did H2 to be 526.12 kilojoules per kilogram, and similarly we can do PR4 divided by PR3 equals P4 divided by P3, and solving for PR4 and substituting, we will have PR4 to be 20.83, and by interpolation we will find H4 to be 651.31. So substituting, we'll have first our mass flow rate. This time will be Q in, which we know is 35,000 divided by H3, we know it, minus H2, we just find it, and this mass flow rate is 55.12. Notice that this is different because we have now different values of enthalpy, because we are not considering Cp constant anymore. Cp is a function of temperature. We can substitute this value of Q in the expression for Q out, which will be mass flow rate times H4 that we just computed minus H1 we found earlier, and this substituting will be 19,907.29. So network will be Q in is Q out. I'm substituting the values that we know. We'll have 592.71 kilojoules per second. So in V, with variable specific heats, our net power will be 15092.71 kilojoules per second, different from A that was 15,772. So this is our second result. In this example, we didn't do all the math, but we have the values, so it's just a matter of putting into your calculator and getting numbers. Thank you, and watch the next video.